Okay, welcome. Today is October 20th, and hopefully we are going to get some Chapter 5 stuff, and I'm hopeful that the technology will work. I've been messing around with it quite a little bit, so it only just seems to work reasonably well when it's in this program. I don't know how to auto minimize it. Let's see if I can do this again. And there, good, okay. So we were talking about transmission line quite a few classes ago, and we've got exact models of transmission line based on a unit length. So we saw how we could write a couple of differential equations, and the differential equations are consisting of hyperbolic sines and cosines, but ultimately we are solving for the sending end voltage and current. If you look at the previous equations, we came up with a way to solve for Vs and Is based on knowing what VR and IR is. So this is all based on the fact that our customers are paying us for a reasonable voltage, right? Plus or minus 3%. So we want to control the receiving end, and then we'll figure out what the sending end needs to be. So that's a little bit of a flip. Okay? Typically when we think about power systems or real-world electrical circuits, we always have an independent power source that drives the result of the circuit. This is the other way around. We know the voltage at the end of the line. We need to figure out what the source voltage needs to be to support that voltage. Okay? So it flips your thinking around a little bit. Hopefully it doesn't intimidate you too much. It's just a slightly different perspective of things. So our transmission now line is just going to consist of a black box. What's in here? We don't care. All we know is that if we can solve for these A, B, C, D parameters, then what that means is whatever's inside the box, I don't need to know what it is. I just need these. This is something you may have seen called the concept of two-port parameters. Anybody remember that in their circuit analysis paths? Where you did a box and you analyzed it. These here are a hybrid two-port parameter, and a hybrid means the units are hybrids, because you can see V equals A times VR plus B times IR. What are the units associated with A? If voltage equals volts, so A times volts, what does the unit of A have to be volts? 1 over volts? So a volt equals 1 over volt times a volt. How about unitless? If there are no units, a volt times a unitless quantity is still a volt. So this has no units associated with it. A is unitless. What about B? What times current equals volts? Ohms, right? So unitless, ohms. Is equals C times VR. What does C have to have for units? What times volts equals amps? What times volts equals amps? Pardon? Oh, mhos, right? If 1 over ohms is a mho, so this is just units of mhos. And then what amps equals D times amps? What does D need to be? Unitless quantity. So this is a hybrid two-port approach because it has a mix of different units. Okay? So, whoops, use this one. Let's start to solve for A, B, C, and D based on our base equations, right? Here's our Vs equation, here's our Is equation. We solved for Vs. We did the hard brute force method to solve for Vs. We didn't do the same thing for IS, but you can do that if you'd like. And here is our form. So in our very basic form, if we just steal these equations, well, we can say what times VR equals Vs. Well, this is hyperbolic cosine of gamma L. So A is just hyperbolic cosine of gamma L. B is ZC. IR needs to be pulled out, right? So that's not the IR. Hyperbolic sine of gamma L. That's my B term. I keep going with C and D, and that's what I go. So for this T model, which means that my transmission line looks like this. You have the A, B, C, D parameters that you need. Okay? Those are the A, B, C, D parameters. But that's not what we typically do in industry. What typically happens in industry is we take this capacitance value that we have over here, and we want to see its effect on both ends. We want to see what happens on the sending end as well as the receiving end. So we break it up and put it into two. And that will allow us to come up with what's our pi equivalent model. Can you shut the door? Please, thank you. This is a pi equivalent. Why do they call it pi equivalent? Looks like the letter pi, right? This is the most common transmission line model that you will see in industry. So because of that, now what we want to do is we can't use the original z's and y's that we did over here. We have to find equivalencies, okay? So we do z prime over 2 and y prime over 2 on each side. All right? So the first thing we need to do is solve from a circuit analysis perspective. So we're looking for equivalencies. Those equations that we had before, we have to solve for equivalencies based on this revised circuit. Because all I'm doing here is coming up with just a bunch of different impedances, and as long as my Vs and my Is results are the same as with this T equivalent, then I'm good to go. I've got no problems. Okay? So we have to do a little bit of circuit analysis first. So I would like to write a nodal equation for this node. Let me make sure I get some ink. I can do that here, I think. Here. Let's do nodal analysis at that node. So I'm going to draw my assumed directions of current. And I've already got IR shown in the out direction there. So the current into the node, this is Vs, right at this node. This node voltage is VR. I know the impedance between it. Can I write a node equation, a current equation for that, knowing that information? It's Ohm's law, right? Vs minus VR divided by Z prime is my first current. That is this current here. Okay? I can do the same thing at this one, right? So I know what the voltage is at this terminal. I know the impedance of this element here. And I'm assuming this is my reference. So it's VR minus 0 divided by, or is it not divided by? What is Y? What are the units of Y? 1 over ohms. So I don't divide my element here. I multiply. This gives me amps. So this current minus this current equals my IR. Okay? Everybody see how I did that? Okay? So let's write another equation, and let's solve for this voltage over here, the V of S. How would you do that? How would you do that? Any ideas? What should I do? what do you do? Think about it. I did nodal analysis here. What do I do over here? No? This one's a little tougher to see, isn't it? It's not so obvious. So it's a slightly more challenging approach. But if I redraw my circuit, and then this here is my VR terminal. Do you see it a little easier there? Right, because my receiving end current does not travel through here. That IR goes out in this direction, okay? So all I'm saying is I need the voltage drop across here, and I need this voltage drop as well. How do I get that voltage drop? I calculated that current. Yep, I have that. But how do I get the voltage drop? Any thoughts? What do you think? Is it too taxing to think about circuit analysis? If I know the voltage drop across two series elements, right? And I want to solve for one of those voltage drops, how would you do that? Use voltage divider. Very good. So if this is Vs, this is Z prime. Now I'm going to throw a curveball for you because I want to be able to use voltage divider. Voltage divider, all the units have to be in ohms, right? So this is 2 over Y prime. I have to invert it because I can't use generic voltage divider with mixing of my terms, right? And this here is VR. So VR is going to be equal to Vs times 2 over Y prime all over Z prime plus 2 over Y prime. So what do I do now? A little bit of algebra. I got a fraction in my fraction, which is not a good thing. So I want to put it under a common denominator. So this is Vs times, oops, not 2, Z, but 2. 2 over Y prime all over, common denominator is just going to be Y prime. So I have Z prime, Y prime plus 2 all over Y prime. Sorry, I'm going to move it up here on the border a little bit and redraw that so everybody can see in the back. Okay, that's what my receiving end voltage is. I invert and multiply. Vs, my Y primes will cancel. 2, Z prime, Y prime, plus 2. Right, everybody see what I did there? Now what I'm trying to do is write an equation for Vs, right? So, just invert and multiply. And then I take my 2 out of my fraction. That is what multiplies my VR term. That is this guy. Oop. My other term comes from the fact that this is what? That has to give me the voltage drop, doesn't it? Across here. So I'm adding this other term here to include that individual voltage drop. Okay? And that's how I solve for Vs. So this is set up in standard form, right? This is A times VR plus B times IR. exactly what we need it to be. Same thing over here for IS, and I'm not going to derive this. This is a little more slogging, but you can get there from here. This is A times VR plus B times IR. So this is equal to A. This is my B term, my C term, and my D term. So when I use the pi equivalent model of a transmission line, I'm going to substitute in Z prime and Y prime, and then rearrange my circuit or my ABCD so I have these terms. You will note A and D equal the same. They're the exact same. Okay? Now the question is, do the units make sense? What are the units supposed to be with A? Unitless. So this is ohms. This is mhos. What's an ohm times a mho? It's a unitless quantity. Who cares if it's divided by 2 or not? This is just one unitless quantity. What's the unit supposed to be with B? What times a current equals a volts? Ohms. That's an ohms. What about C? Supposed to be mhos, right? So this is essentially going to have the same units here, which is unitless. We end up with a Y prime in the front, which means it ends up with the units of mhos. And then we've already determined A, and since A and D are the same, we're good to go. So everything checks out. Our units are fine. Okay? Now, there's another way we can do that. And this one, if you've done 2-port parameters, this is probably the way that you were taught. So I'm going to draw my pi equivalent. Here's my pi equivalent, y over 2. This is z prime. Y prime over 2, I'm sorry, not y. This is VR, IR, VS, and IS. And if you remember, it's VS equals A, VR, not B, sorry, plus B, IR. This is a linear system. Linear system means if we can solve for any of the unknowns at any specific point on the curve, right, anywhere, then that will hold true for all conditions or cases. So let's use our heads for a second. Looking at that equation, VS equals AVR plus BIR, is there a way that you could get rid of an unknown? I want to solve for A, let's say. I got to get rid of this part. How do I do that? What if I make IR equal to 0? What happens to B times IR? Becomes plus 0. So VS will equal AVR when IR equals 0, right? So when does IR equal 0? Under open circuit conditions, which is, if you remember what we drew, right? If we have our circuit, there's no current exiting out, right? And what we said is this is just VS here, right? That's the plus minus VS there. So essentially what we did is we said I here. Hopefully people can still hear me. Sorry about that. I has to be equal to 0. So when I is equal to 0, you can solve which means it's just a simple voltage divider. That's it. So that's how you can use 2-port. How about B? How do we solve for B? maybe we don't know what A is. If you have this equation, how would you solve for B? You got to speak really loudly. The helicopters have taken off. Yeah, if I say that VR equals 0, right? What happens to A times VR? This is 0. So B equals VS divided by IR when VR equals 0. How do I make VR equal 0? Put a dead short circuit across here. So now my circuit looks like this, right? This is my Z. I've got a short circuit here that shorts out the capacitance to ground, right? This is VS. And my IR is going through here. So isn't it just Ohm's law that VS divided by IR equals Z prime? Doesn't that match right here? Isn't that consistent with what we expect? I hope so. So you can do the two-port parameter approach instead of doing circuit analysis and saying, let's do Kirchhoff's current law, nodal analysis in the original circuit. Usually you can simplify your circuits down quite a bit by recognizing, hey, let me get rid of B or let me get rid of A and then solve the rest of the parameters. In either case, you're either going to put an open circuit or a short circuit, and that'll take care of it. Let me douse some noise, see if I can do that. I apologize. Somebody set it up to 80 degrees here. Maybe that's a little warm. Sorry, Taylor. I was starting to pass out up here, so you guys are all dressed. Can you hear me now? Good. Questions on that? Because we now have A, B, C, and D to solve any real-world pi equivalent transmission line. That's our A, B, C, D. The only thing we need to do is solve for A, B, C, and D in terms of those original parameters. So what we need to do is take our T equivalent, which is cosine hyperbolic of gamma L, and that's Z sub C. It's hard to see over here. Sine hyperbolic of gamma L. That's 1 over Z sub C, hyperbolic gamma L. And then this should be the same cos gamma L. This is our T equivalent, which is our exact model that we came up for. This, because it's VS IS, has to be exactly the same as 1 plus Z prime Y prime over 2, Z prime Y prime, 1 plus Z prime Y prime over 4, and 1 plus ZY over 2. Those two have to be the same. All right? So pretty quickly what we can see, let's solve for Z prime first, because that has to be the same term, right? It has to be equal to Z sub C sine hyperbolic of gamma L. That's all you're doing. You're setting them up to be the same, because even though it's a T equivalent, remember, these are equivalent to each other. So VS and IS have to be the same whether you're using a T or a pi equivalent, given the same VR and IR. So that's all we're doing here, is we're setting up the equivalencies, and you can just pull out Z prime there. That's what's happening here. Okay? Everybody see that? To solve for Y prime, we have a little more work to do. We know that A is hyperbolic cosine of gamma L. which is equal to 1 plus z prime y prime over 2. We're going to solve for y prime over 2. Not y prime, but y prime over 2, because our model actually has y prime over 2, right? Why would you solve for y prime if you have to go back in and rewrite it and divide that by 2? So all I need to do is substitute. I solve for y prime over 2, and I substitute in my z prime, and I end up with 1 z sub c. And what I've done here, that is a hyperbolic trig identity, which tells you that it is the hyperbolic tang of gamma L over 2. That's all that is. Okay? So now we know how to solve for z prime. We know how to solve for a prime based on our original circuits. And we can solve for a, b, c, and d. That's it. We got it all. We have everything. Yes, ma'am?
What are the benefits of doing the first way you described it versus this way?
The t?
It's a lot easier than the first way. So why would you do it?
It's a good point. So I think what she's getting at, let me repeat it just.
Yeah.
So this is the original t equivalent model that we have. This is the pi equivalent model. And the question she asked was, why bother doing this when this seems easier? It's actually much easier to solve these equations here, to write actual equations and solve for them very simply. Well, I shouldn't say very simply, using these hyperbolic sines or cosines. If we did the pi equivalent and tried to do it per unit length, it's a much more arduous process. So we solve for it more straightforward, and then we do the equivalency to get it over here. That's all. Pardon? What you'll do in industry is you'll just recognize this is my pi equivalent, and I'll just substitute this. I'll solve for z, and I'll solve for y over 2. That's what you would do at industry. Those are the parameters that you would get. Okay? So just a little more simplification. We can do a tiny bit of substituting, and then we say that z prime is equal to our original value of z times hyperbolic sine gamma L divided by gamma L. That's a little bit easier, and we'll see why it's easier in a second. And we're going to just define z as the entire impedance of that line. Remember, if we use the t equivalent, we'd be using the ZL, but this is the pi equivalent, so that's why it needs to be adjusted with those hyperbolic sines and the gamma L's to make it equivalent. That's my z, that's my y, or my y prime. And the biggest advantage is you've got a z and a y over 2. These two terms, right, fall out of our original equations just by multiplying by the per unit length, and we have what's called a scaling factor. It scales the magnitude and it phase shifts the result. That's what ends up happening. Okay? So these are written based on the original ones plus a scale factor. And based on the unit length determines how hardcore we need to be. So if we take a typical unit length of 50 miles, if we take hyperbolic sine of gamma L divided by gamma L, what is this number right here? That to me looks close enough to 1 at an angle of 0, doesn't it? So how much scaling needs to be done for a line that is 50 miles or less in length? Nada. Not for z, because the sine hyperbolic gamma L over gamma L doesn't change the magnitude or the phase shift, as does that one. That's essentially 1 at an angle of 0 as well. So for a short line, what do? If it's a short transmission line, we're actually going to take our pi equivalent And instead of these being y primes over 2, they're just y over 2. And this is, instead of z prime, it's just z. So that's a lot easier, right? Remember all that stuff about hyperbolic sines and cosines? On a short transmission line, this is just little z times the length. That's it. There's no hyperbolic sines or cosines. And what we'll also see is that this z value is so much greater than these two that for a short transmission line, that's our equivalent circuit. We don't even have those shunt admittances on the front and back end. We can neglect them. So for a short transmission line, you just have a z. That's it. There's no y prime, there's no y. Those get erased. If it's a medium length line, 50 to 100 miles, that still looks pretty close to 1 at an angle of 0 to me. So I'm going to stick with that fact that this is 1 at an angle of 0. So if it's a medium transmission length, the only difference is these shunt admittances start to have more of an impact. So you have to include those into the model. Okay? If it's longer than about 200 miles, this is a 3% error. That's getting to be pretty significant, right? Because when we want voltage drops to be within plus or minus 3% at the end of the line, we're getting to be 3% in error in our calculations. So that's probably is not going to be the case. So if it's a long line, what we need to do is these go back to z primes and y primes. Okay? So let's summarize. Here's a short, medium, and long. So this is less than 50. This is generally between 50 and 150. And this is usually greater than 150. So I only have a z term here. I only have a z term here, and that's it, nothing else. Over here, I have a z and a y over 2 on each end of the pi equivalent. On the long line, I have to use z primes and y primes over 2, which means I need some hyperbolic sines and cosines. I have to go back and get those really detailed equations. Okay? That's how you analyze transmission lines of varying lengths. And here's the key. If you have a short line and you want to use hyperbolic sines and cosines, it's still right. It's actually more accurate, isn't it? Because you can see it still does a slight magnitude and phase shift. So you can always, always, always use the exact equations for any length of line. Always. If you have a short line, you can simplify it just by using z. Makes your work a lot easier. If you have a medium length line, you need to use z and y over 2, but no hyperbolic sines and cosines. If it's a long line, you need to use the full Monty hyperbolic sines and cosines. But you can always use hyperbolic sines and cosines for any of the other ones. It just depends on the amount of work you want to do. Okay? So that's just kind of summarizing what we just said. Okay? So here's an example. A 345 kV, three-phase, 130 kilometer transmission line has an R in ohms per kilometer, an L in millihenries per kilometer, and a C in microfarads per kilometer. Here's the key thing here. It's highlighted all per phase. But remember, there's no such thing as a three-phase impedance. You should know that by default, or maybe hopefully you will know that by default by the end of the semester. But that is a requirement. You cannot have a three-phase impedance. So this is something to think about and highlight in your notes. The bell should be going off saying, oh, these are per phase impedances. So what voltages and currents should I be using in my analysis? Single phase quantities. Is 345 kV a single phase or a three-phase quantity? It is a line-to-line quantity, right? So it's effectively looking at voltages across two lines. So the very first thing you need to do is divide that voltage by the square root of 3. Okay? Muy importante. I don't know if I said that right. I don't know. You probably heard that on the radio. If I say bad French, Spanish, I don't even know what language I just spoke. It's not to embarrass anybody. It just means I'm being goofy. So I apologize if I offend anybody. Receiving end load is 270 MVA at a 0.8 power factor, lagging, and its nominally voltage at the receiving end is 325 kV. Okay? So, if that's confusing, draw a picture. 130 kilometers. Is that a short, medium, or long line? So you can usually multiply by 0.6-ish, right, is to go from kilometers to mile. So 0.6 times 130 is 78-ish. Did I get that right? So where does that fall here? Medium. So we have to solve for z and y over 2. So let's draw my equivalent circuit. This is y over 2, and z. Do I know the voltage here? This is the receiving end. This is what the customer is connecting to. This is what they're paying for. So what's the voltage there? 1 point? 120? Boy, that would be scary. It's 325, right? Or is it 325 divided by the square root of 3? Remember, we have to work in phase quantities. This is a single phase capacitor. If I put 325, that would give me wonky results. So I have to convert that to a phase quantity, divide by square root of 3. And since there's no other point of reference, since this is the end of the line, let's make that 0 degrees. Got to start someplace. Let's put 0 at the receiving end. Now, I need to solve for my current going to my load, or my receiving end current. And remember, S, 3-phase, equals square root of 3 V line, I, line or phase conjugate. So I line is equal to S 3 phase divided by 3 V line conjugate. S 3 phase is 270 MVA. So this is 270 MVA. What is the inverse cosine of 0.8? 36.7? And it is a negative number. Why did I put the negative 36.7 there? It is a lagging power factor, which means what? If it's a lagging power factor, the power triangle is flipped up. Then I've got to take the conjugate of that, the complex conjugate, which means I got to put a negative. I'm going to pause for a second because I'm relying on a lot of understanding of power triangles and stuff here. So I really want you to think about what I said and truly understand how did I end up with, negative 36.7. Sorry about that. Make sense? Don't make sense? Who doesn't make sense? Pardon?
If you're looking at the capacitance, wouldn't it be a leading power factor?
The capacitance is associated with the transmission line, right? What is the 270 MVA? What is that? Read the sentence. The receiving end load. That has nothing to do with the T line, right? So if you notice here too, I also showed IR. It's after the transmission line, right? So it has nothing to do with the transmission circuit. The transmission circuit will change the power factor, but it's on the load, so it hasn't even seen the transmission line yet. You need to calculate that. Does everybody understand why I got a negative 36? I haven't finished solving for it. I've just put S in there. I'm just trying to make sure everybody understands why I get the negative 36.7, but you're right. I do need to add that. I don't want to put more on because this is relying on you all knowing a lot of what we've done so far, right? If this does not make sense, speak now or forever hold your peace, right? Everybody gets it? That'd be awesome. Ricky, feel good? Okay. So then, whoops, I divide by the square root of 3 times 325 kV, and I take the conjugate of 0, which means it is 0. And the current that I calculate is 490, let's just be lazy, 480 at an angle of minus 36.87. That is what IR is. So, I plug it into my little matrix system here. I know what VR is. It's 325 kV divided by the square root of 3 at an angle of 0, and IR, which is equal to 480 at an angle of minus 36.9 amps. Now I need to solve for A, B, C, and D. A, we said, was 1 plus y z over 2. Notice, I no longer have y prime and z prime, right? Because in a medium length line, the hyperbolic sines and tangent disappear. It's 1 at an angle of 0. So I need to solve for y and z, and I'm good to go. So I've got r, which is going to be a part of my z. I've got L, which is a part of my C, but I've got to go ahead and put it in terms of a reactance, a complex reactance. I know what C is, but again, I need to make that a complex admittance, which means it has a J term and has the unit of mhos. So I can't put capacitance in there. So each one of these, excuse me, I need to solve for its reactance. So here, it's omega L equals 2 pi FL, 377 times L, and I need to get it in ohms, not ohms per kilometer, so I multiply by the length, and I end up with 39.2 ohms for my reactance on my line. For the capacitance, which is going to be an admittance, it's 1 over 2 pi FC, 377 radians per second times the farad value times the line length gives me 1821 ohms. I solve for Z, so it's just going to be my resistance, which is 0.36 times 130, 4.68. And my J term is going to be stolen from here, and since it's an inductor, I put a positive J. That's my Z. My y over 2, not my y, but my y over 2 is just going to be equal to, excuse me, if I have a Z term and I invert that, I end up with y, right? So I take this term, I invert it, then I divide that by 2, and I end up with my y over 2 term. So I kind of combine that here in one step. You invert this term, 1821, divide by 2, and you should end up with 0.274 millisiemens, right? Put the J term, but this is a capacitor, right? Why do I have a positive J? I thought capacitors had negative J's. Is that a screw up? You know I didn't screw up because I even rotated the ohm symbol, right? So if I get that kind of attention to detail, you know I didn't put a negative J when there should be a positive J. So why did I put a positive J? Right. So Z for capacitor is minus J over X sub C. No. Not over X sub C, times X sub C. And 1 over Y is 1 over J X sub C, which is equal to J 1 over X sub C. So when you bring the J term to the denominator, it becomes a positive J term. That's why you should only have positive J's. Okay? Then I just plug and chug. A and D is 1 plus Z times Y over 2. Gives me 0.989 plus this term. B, which is equal to Z, which is 4.68 plus J 39.21. And C, so this is where you can see, like, sometimes we ignore the C. Look how small my value of C is. Minus 35 mics plus J 005. So if I invert that, that's going to be a really large number, right? So there's not a lot of current and not a lot of reactive power going in or coming out of those capacitors. But this is where MATLAB is really easy or nice, useful to work with. Or if you all are using your TIs to do that, I would encourage you to set up in your TIs, set up an ABCD matrix, and then let it be equal to a Z and a Y term, and then just solve for your Z and your Y each time, and then update your ABCDs. Because these get to be really crazy small, and it's hard to write them. But if you store it in your calculator, it's not so bad. Okay? We've already done the power triangle stuff. We know the current. Whoops. Now we can go ahead and plug and chug. So these are our parameters. And what I end up with is a sending end voltage of 199.19 and a receiving end, a sending end current of 421.13. Well, anybody have any problems with that? My receiving end voltage is 325 kV. How in God's name do I get a voltage on the sending end that is less than the voltage on the receiving end? Yeah. You need to really multiply the magnitude of this by the square root of 3 to really get that. How about the current? What's happening with the current? Well, it goes to what Russ was saying before. Hey, you got all these capacitors in here. Remember, capacitors put Q back into the system. So as long as the Q that is being supplied by the capacitors is greater than the Q that is being consumed by the reactor in the line, then your current magnitude will actually drop. And correspondingly, your voltage magnitude, I also think, will drop as well. And then we can draw our phasor diagram. You'll notice that VR is what? Well, VR is the reference, so it's at 0. IR has a lagging power factor here. That matches. VS has a greater magnitude and a positive angle. Anybody here in this class who took 321 with me, tell me anything about magnitudes and angles? We did it in synchronous machines. So we have our thinking caps on. So the magnitude over here is higher than the magnitude over here, and the angle over here is higher than the angle over here. If the magnitude is higher than here, then that tells me that Q is flowing in that direction. It's flowing from this side to this side. Not all the Q is going to make it in there because I'm going to consume some in the line, but the reality is that Q goes from a higher magnitude to a lower magnitude voltage. Okay? So Q is indicated by the magnitude of V. P is indicated by the magnitude of the angle of theta. So if this angle theta is higher than this angle, then what does that mean? Power flow, real power flow, is from the higher angle to the lower angle. And that's the case when your X over R ratio is sufficiently high enough in your system, which is almost all real world power systems have that. So I could look at a diagram with bunches of voltages on it, and I can tell you just by looking at that diagram, where do the power flows? Or where does the power flow? Both Q and P, just by looking at magnitudes. I don't even need you to calculate the P and the Q. I can figure out overall directions just based on that. And so that's what a lot of people will do. They'll just say, hey, what's the voltage at this end? It's too low or too high. That means there's too much power, reactive power flowing in that direction. So they'll try to switch in some cap banks. That will boost the voltage up on one end, which means you don't have as much reactive power going in that direction. Remember we talked in this class a little bit about phase shifting transformers? Same idea. A phase shifting transformer will, all it'll do is introduce different phase shifts between this end and this end, and its whole purpose in life is to reduce power flow in that transmission line. So that's why they use phase shifting transformers. It's just to change the angle so you can either increase or decrease the amount of power flow from bus 1 to bus 2, for example. Okay? You can check that out if you'd like. Then the last thing is input power and power factor. Okay? Questions on how to do a problem like this? Any questions? So this kind of summarizes it a little bit. What if we change the load from a lagging power factor to a leading power factor? So the first thing we have to ask ourselves, all right, is this figure, do we buy that this figure is reasonably accurate for us? Does the top figure look like it has a unity power factor? Who says yes? 1? Who says no? 1? All right, so some brave souls. Let's start out with you, Ben. Why do you think that this does not have a unity power factor?
Because it has an angle associated with it still, so it's the inverse cosine of the angle.
Okay. Russ. Troy.
I said it's unity because the receiving end things are in phase, the carrying voltage.
So listen what he said. The receiving end voltage, is the current in phase with the receiving end voltage?
What's that?
Anybody else? Are the two angles the same? Doesn't that mean that they're in phase with each other? If this is IR and this is VR and there's no distinguishable angular difference, the two are in phase. So, what is the inverse cosine of 0? One, right? What kind of a power factor is 1?
Unity.
Unity. So do you agree now that this is a unity power factor? Okay? So essentially now what happens is, because it's unity power factor, the reactive power going to the load is non-existent. All we have to do is support whatever line charging that is required, any reactive power consumed by the line. So the magnitude of Vs, if at all, is going to be slightly greater than or slightly less than the magnitude of Vr, because none of the power, reactive power, is really coming from the sending end. But look at the angle between Vs and Vr. It's still positive. So that means power is still flowing from Vs to Vr. And since this IR, it's a little hard to see. Maybe I can draw the little angle symbol here. Let me see if I can recalibrate the board, because that was off by 1.5 miles. Sorry about this. All right, let's erase that and see if that comes out a little better this time. So this is where it is. Oh, much better. We still have a magnitude of IR, which means that there's current going through, which means there has to be real power flow, because it's a unity power factor. So power is going from the sending end to the receiving end. That does not change. Okay? And in the case of a leading power factor, what does that tell us about the load? It is more capacitive than inductive. And we say capacitors supply reactive power, inductors consume it. So keep that in the back of your minds. Is this a leading power factor condition? Let me draw the IR here. Would you agree that this is a leading power factor?
Yes.
Okay. So what happened to the magnitude of Vs? Is it less than or greater than Vr? The magnitude is less. Now that means that Q is flowing from the receiving end to the sending end. Anybody have a problem with that? Reactive power is just borrowed power, right? It goes out and it comes back. It goes out and it comes back. It just goes out and comes back at different points on the waveform, and that's how it can support the voltage. Okay? Think about it in terms of a capacitor. What do you see in a capacitor first? Current or voltage? When you energize a capacitor, what do you see change? Current, and voltage doesn't change, right? So the idea is that there's current going to the load before the voltage builds up, so that current is starting to provide or discharge back to support the voltage. That's why you get that reactive power support. So your voltage magnitude, Vs, can be less than Vr in steady state. And power is still flowing from the sending end to the receiving end, because just because I have a leading power factor here doesn't mean I've added a generator on this side. So power still has to flow in this direction, from sending end to receiving end. Does that figure still validate us? Does it seem like it's accurate? The angle associated with Vs is more positive than the angle associated with Vr. So therefore, it's the case. And this, if you had taken a previous class with me, isn't it exactly the same as in synchronous machines? When we talked about excitation systems, that's how synchronous machines work. What's the X over R in a synchronous machine? It's almost infinite, right? X is much, much higher than R in synchronous machines, and oftentimes you don't even bother showing the R. It's so much smaller. So this sort of validates what we would expect. All right, you got 5 minutes? Little in-class quiz. Time for a little in-class quiz. 5 minutes, is that enough? I'm available for questions if anybody needs it too. Phone a friend. Is that show still on? I don't even remember the name of the show. Who Wants to Be a Millionaire? That show's still on?
Yeah.
Wow, that show's like 20 years old, I think. I think Regis Philbin is he still the, wow. That's what happens when you don't have TV. You don't really know what's happening in the real world. Well, let me get you started at the very least, in case you haven't. So, the VR is equal to 345K divided by the square root of 3. Remember, there's no such thing as a single three-phase impedance. So we have to break that up into a single-phase voltage. I have given you IR. So IR is equal to 400 at an angle of inverse cosine of point. Pardon? Oh, I gave you the sending in voltage and current. Sorry. Other way. So this is 345 at an angle of 0. This is over square root of 3. Sorry. This is 400 at an angle of minus the inverse cosine of 0.8. 0.95. So now you know so you solve your A, B, C, D parameters, right? And you don't even have to do all the multiplication and division. The only question is, do you need to know what gamma and L are? Why not? Yeah, but remember, if I did the exact equations, it's zy times hyperbolic sine of gamma L, and then the tan hyperbolic of gamma L over 2, I believe. So do I need to give you the gamma and the L here? Giving you the L, do I need to give you gamma? What were the rules about the length of line? If it's a short line, we can use Z and that's it. If it's the medium length line, we can use Z and Y over 2. And that's it. If it's the long line, we need to use Z prime and Y prime over 2, which requires us to use gamma. Is this a short, medium, or long line? Medium line. So, you don't need to do that here. So you solve for your A, B, C, D. Then you can invert and back calculate your VR and your IR. Okay, I didn't give you the answer to that, but you can practice that. Do you want to collect it for next time? Would that be good, or should I collect it right now? Do you want to have that as a homework due on Thursday, or?
Yeah.
Okay. All right, let's have it due Thursday then.
Extra credit.
No. Extra credit means you do a couple other problems. Then I'll give you extra credit. How's that?
Do you really give us extra credit in this class?
Depending on the circumstances, yes.
So we just like bring
If we got a bad word on the test.
there's some problems. You can't make it.
Maybe. Depends. Depends on the quality. I mean, I have to make it fair for everybody. So, I have to be able to compare your stuff to other people's stuff. It gets very difficult. Generally, if you want to do extra credit, it would be like you need to write a paper on something or not just doing problems. Okay? I still have 5 minutes, so let's finish up. So our power and transfer for short transmission lines, now we just have our Z term, right? We have no Y's over 2. So our S, so we're going to draw this as a black box, and we have S1 to 2 just means power flow from bus 1 to bus 2, and 2 to 1 just means from bus 2 to bus 1. It can be a negative number. It doesn't have to be positive. So let's solve for S12, which is V1 I1 conjugate. We're not going to worry about 3-phase or single phase. It could be done in per unit. So I substitute in my term for I1 because all I have is an impedance, right, a Z term. And I do some fancy math, and what I end up with is V1 squared divided by Z at an angle of theta Z minus V1 V2 over the magnitude of Z, theta Z plus theta 1, 2. If we just treat it as an X, no value of R, okay? What that means is Z here, if it's purely inductive, what's the inverse tangent of X divided by R when R is 0? It's the inverse tangent of infinity, which is 90 degrees, right? So theta Z becomes 90 degrees. And what we can do is some substitution, and what we have is P1 to 2 is V1 V2 divided by X times the sine of the angle between theta 1, 2. For the most part, this is the equation that we will examine to simplify our power flow. And the max power that we can ever transfer is when the sine of theta is equal to 1. So if you look at a transmission line, your power flow typically follows something like this. 90 degrees, 180 degrees. This is P max. That's the maximum capability based on the voltages. Regardless of, hey, is this exceeding the capability of the line? This is max what I can do based on those voltages. So remember how we said, look at the angle? What's the biggest predicator of how much power flows in a line? Well, you can see the magnitude of the voltages have some influence, but again, those aren't going to vary more than plus or minus 5%. What if my angle here is 0? I don't care how much the voltages are, right? There's no power flow. You can see I can make a huge impact on the amount of power flow in a line just by running it at a greater angular difference between the two. So this is the limit. This determines stability of power flow through a transmission line. This is a very important equation when you're assessing stability. We've talked a little bit about long lines being stability limited. That's because of this equation. And what happens if you run your line over here? Well, if somebody wants to increase the power flow, at some point it reaches its peak and then it actually starts to go down. What that means is your frequency starts to drop, and it is exacerbated if you can't get your angle back below 90 degrees. So at some point you'll lose synchronism. You'll actually go out of phase and you'll cause massive problems. Something you want to avoid at all costs. We talked a little bit about some of the thermal limits for power transfer. This is for shorter lines. If we can run these lines at a much higher temperature, right, that can dissipate heat better, then we might be able to get shorter lines being able to move more power because those are thermally limited. This is pretty interesting, right? Most of the time you shouldn't run your conductors anything above like 120 to 150 C. That usually is like a 40 degree C ambient with a 90 degrees C rise before you start getting issues. You can push 200 C on these conductors because they can dissipate heat really well and they're super, super strong. They don't sag as much. So that's some of the advantages there. Okay? We talked a little bit about the stability limits in terms of angle. Can't exceed 90 degrees. We also have limits in terms of voltage. At some point in our system, if we look at a capacitor, these are called nose curves. So if I try to move more power, my voltage starts to drop, but it kind of drops linearly until I get so much power demand that it kind of comes back. See why it's called the nose curve? And it all has to do with there's some critical point where the voltage across this is no longer able to sustain the reactive power demand in the system. So that's why it starts to go back down. That's voltage stability. That's sort of a newer area of understanding. And then this transient stability stuff has a lot to do with that power angle, but it's more about machines moving in real time. And then how do we do compensation? How do we make a line better? Because if we have V1, V2 divided by X, we can move more power if we drop the value of X, right? So if I have a transmission line here, what if I put a series cap in it? There used to be a series capacitor in Orrington, and its whole purpose in life was to reduce the value of Z seen by the transmission line. I don't think they use it much today, or if ever, but is that a series cap or is it a shunt? I don't know. But series capacitive actually helps improve the impedance of the line. Sometimes you put an inductive element in there because at night when it's very lightly loaded, the voltages can be sky high, way too high. So you can actually decrease the voltage on the end of the line by putting some inductance to it. And then these new flexible AC transmission systems, everything's an acronym, but this is one of the sillier, stupid ones, FACS, right? Flexible AC transmission systems. They'll use much more sophisticated pieces of equipment. Static bar compensators, which basically have a bunch of inductors and capacitors and are switched in on a continuous basis, up or down, to monitor and maintain voltage. You can get like in Chester, anybody been to Chester? There's a static bar compensator there. It's probably about 50 minutes from here, I think. They have a static bar compensator, and its whole purpose in life was to inject or absorb reactive power to increase the flow, real power flow, of the transmission lines that come in from Warrington. That's what it was. It was a 40 MVA, I think it's 40 MVA, but its whole purpose was to increase power flow when there was originally only one line. It still works, they still use it, but it's not as instrumental as it once was because there's two lines coming in. And that's it for Chapter 5, which means the homework for Chapter 5 is due 1 week from today. We have lab Thursday morning, which you'll be doing more modeling of transmission lines. I would encourage you before you come to lab, try going through the lab, see if you can get results based on what we do. I would do it for both. I would try the short line and medium line before you come to class or lab. And if you want to see how mad your skills are, you can try the long line. You can do all three cases and see what you think. Okay, that's all I have. Have a great day. I'll see you on Thursday.